Good. Okay. So good afternoon, everybody. So I'm Sari Awad. I'm professor at IMT Atlantique, and I'm honored to moderate this discussion this afternoon. Okay, we will have now 4 presentations on sustainable aviation fuel for different technologies we produce. So we'll start with the first presentation with Julien Grandjean, project leader at IFP Énergie Nouvelle. So Julien is a process engineer at IFPEN and a project leader in energy products, a business unit. He has been involved in a biofuel project between 2018 and 2021, and since 2022 he's leading the project Biojet at IFPEN. So a few words about IFPEN that develops low carbon solutions for transport and industry, for applications still relying on liquid fuels such as aviation. IFPEN proposes a portfolio of frontline technologies for advanced sustainable fuels processes and production, including hydro-treated bio-oils, advanced biofuels, and e-fuels. So Julien will present their portfolio now and the different pathways. Thank you. This is the
Thank you.
micro.
Okay. It's in English. Hello, hello everyone. So I'm very glad to be here to present you with this technical view of what we do. We are a public research and innovation institute and training organization. Also, we have 4 strategic priority in renewable energy, mainly for sustainable mobility, and more also for protection of the climate, the environment, and circular economy. And we are still keeping an activity in our traditional field of oil and gas, where we are leaders with our partner Accence, with selling the innovation of IFPEN, who brings our technology to the market. We have two sites in France, more than 1,500 employees. Most of them are research scientists with PhD students. Fundamental research is the backbone of our innovation and supports all this innovation that I will present. So, coming to low carbon fuels, we believe that low carbon fuels are a part of the solution to reduce the problem of climate change, and especially for transport where it is difficult to decarbonize, such as aviation or marine fuel. We have this mandate for the RED of 5.5% of final energy in transport, so it's tomorrow. And we have to provide efficient solution to reach these targets. We have a long time history with Accence to develop this innovation, starting in the 90s with the first generation biofuels, which is based on the SAF technology, esterification of vegetable oils. In the same years, we started the development of gazelle, which is our proprietary Fischer-Tropsch technology. At the end of the first decade of the century, we started the development of two major projects, Futurol and Beauty Fuel, which has the two core technologies for production of ATG and Fischer-Tropsch biofuels. And these two major demonstration projects ends in 2018 and 2022, and we are now in the process of first industrial demonstration and commercialization of these technologies. So we have four pathways to produce SAF. The most mature is HVO, hydrotreatment of vegetable oils, which is mainly a two-step process, which is ITRL. We have almost already 13 references of plants which are already producing SAF or under construction. Then we have these two main pathways for second generation SAF production. That's to say the BTL or EBTL, with addition of hydrogen, renewable hydrogen, but based on the gazéification step and the Fischer-Tropsch reaction. And we have, based on Futurol, this ethanol and ethanol to jet production, production of ethanol and then dehydration, oligomerization. That's called the jetanol, and we get a first reference in the US in collaboration with Givo. And the e-fuel, we enter in the competition also for e-fuel production. We have here three flagship projects, and we are competing in this map where you see many projects in Europe which are announced. The problem is that no one for the moment gets the final investment decision, and it is really we are working very hard with our partners to have at the end of this year or next year a final investment decision, especially for the Bio360 project or the Nacre project in south of France. We are also part of the Take Care projects, which not far from here is planning to produce 15,000 tons per year of e-fuels based on CO2, CO2 waste from cemetery production. What are our challenges ahead of us in the coming years? First and foremost, we have to get this final investment decision, and for that we need to reduce the costs. Reduce the cost means develop more efficient processes and catalysts with disruptive pathways. It means also have a diversification of resources. We see that clearly in the Bio360 project, concretely. To optimize biorefinery and also increase the fuel incorporation rates in fuel pools. So we are working on these challenges with 4 research programs which are described here. I will focus on the production of synthetic fuels through the thermochemical pathway, in which I am being more involved. So this BTL technology, BTL means biomass to liquid. We have here a map with different projects in the world. For the moment, there is no real plant working on this scheme, but so we need to process lignocellulosic biomass, which means residues. It's not entering in concurrence with food production. This biomass is gasified, converted into syngas, which is processed through the Fischer-Tropsch reaction and upgraded. The strength of this process is that it is based on our knowledge with accents on the Fischer-Tropsch synthesis. This is a proven technology, special technology developed at IFPEN on cold flow models, and demonstration units which has been operated in collaboration with Eni in the year 2000, producing 20 barrels per day, 25,000 hours of production. So fully demonstrating our slurry bubble FT technology. And then we have the upgrading units with well-known, well-optimized IFPEN and Accents processes with catalysts for all these reactions. So we are able to achieve production of diesel and under specification in different mode. Maxi diesel, of course, is not our subject, but we turn to Maxi Kero. Now we guarantee 70%, and in the very close future, we hope to be able to provide 80%. When we talk about e-fuel, we have to keep in mind the objective to reduce by 65 or 70% the CO2 index. This target is quite well achieved with the Bio360 technology. You see that we get a 90% saving, the remaining emission coming mostly from the biomass supply. So that can still be optimized by local sourcing, utilization of more waste, and so forth. So in terms of feedstock, we have a diversity of feedstock which can be applied to the gasification. Thanks to the pre-treatment, which has been demonstrated. Pre-treatments, the purpose of a pre-treatment is to get a torrefied biomass, which can be easily grinded and processed through the gasifier and concentrated in energy also. So the gasification technology is provided by our partner, UD, ThyssenKrupp. It's untrained flow gasification, having the main advantage to be under pressure for the downstream units and with pure oxygen, operating with pure oxygen. and producing saturated syngas for the downstream reaction. Here to give you a view of what we achieved through the Bio360 project. We managed to build and operate two major demonstration units in the north of France. One near Compiègne, which operated continuously for 100-500 hours, producing 2 tons per hour of torrefied biomass. And also demonstration plants in Dunkirk, when we processed the biomass which was torrefied in the net, and also other biomasses. And then this, you have a grinding, you have a grinding units and gazéification units and processing of the syngas, just feeding a FT plant pilot here. We can increase the yield of production, and we can double the SAF production by 2 just by, I would say just, but it's quite costly, but it's economically interesting because you are doubling the production of SAF by injection of hydrogen to get the good ratio for the FT production. So you avoid water-gas shift reaction and CO2 production. Here some figure of our flagship Bio360 project. Bio360 is a project who started with Elise Energy, with supporting the project and with the leader on the project, which aims to produce 75,000 tons per year of e-biokerosene in the south of France, representing 15% of demand in the time when it's supposed to start. Of course, we have to get through the final investment decision, and we have gets some milestone with a public consultation, which was not an easy task, but which helps to improve also the project, the feeding plan, which is very important to have some diversified feed supply. And it's also very important and supported by the local people, because it is an opportunity to be sovereign in terms of SAF production in France and to create a job in this area. I will conclude to say that we are not alone. IFPEN is active in a network with a lot of public players, public authorities, and also industrial partners to succeed in these challenges. So we really think that SAF is an opportunity for France, and we work to meet these challenges. We have the opportunity to talk about that in this debate. Thank you.
Thank you. Thank you, Julien, for the presentation. In the audience, do you have some questions about the technologies developed by IFPEN? Yeah, maybe I have one question about the production costs of the different technologies that you have presented. They are in the same range, or you have different? I think it's not working this one. So.
Yes. It's working, yes. Of course, all these SAF, they are more expensive than fossil fuel. When we talk about HVO, it's I think I have some backup slide. Oh, yeah. Here we are. This is some indication we have taken from a roadmap from decarbonation. You see that the HVO is around 2,000, a little bit less euro per tons. The BTL and EBTL with a larger uncertainty for the EBTL, depending on the costs of electricity, which is a very significant part of the breakdown. We can see here. It will be around 3,350, quite comparable to the alcohol to jet. And the e-fuel, it's another order of magnitude, I would say, around 300 to 600. Also very dependent on the cost of electricity, but with also a part of capex which is not negligible.
So with the biofuel to liquid, you have more uncertainties. Is it related to the feedstock that you are using? The cost really, what's the contribution of the feedstock in BTL, for example, in the whole cost of the...
You see that the feedstock represents here around 20% of the cost.
Yeah. Okay.
So it will be also strongly dependent on the cost of the biomass, of course.
Okay.
And there is still efforts. You see that we have a big, for a capacity like a biotigent, and the investment only for the BTL part is around 1 billion.
Okay. Yeah.
So it's a big investments, and that explains why you don't see so many investment decision today.
Okay. Thank you very much, Julien. Now we pass to our second presentation that will be presented by Frank Lightart, the Vice President of SFW. He will explain to us what is SFW. So he leads the circular carbon business, and he has a mechanical engineering background with 25 years of experience, and actually he's focusing his expertise on the gasification and combustion of biomass waste, along with a deep understanding of carbon capture technologies. So, Frank, the floor is yours.
Thank you, Sari, for the kind introduction. And hello, everyone. Welcome to this session. Really good to see so many of you interested in sustainable fuels. So my name is Frank Lightart. I represent a company called Sumitomo SHI-FW, where I'm heading the so-called circular carbon business that is focusing on gasification for sustainable fuel applications and carbon capture. And today I would like to give a short introduction into gasification for unlocking sustainable fuels. But before going that, a short introduction into who we are as a company, as you may not recognize the name. So SFW, we are a global technology provider for integrated solutions for decarbonized energy. As it reads here, we serve our customers with about 1,800 people located in Europe, Asia, and North America. And we are part of the Sumitomo Heavy Industries Group, headquartered in Japan, but our roots are very much into other companies, Alström from Finland, and you may recognize the name Foster Wheeler from the US. I guess we are best known as the market leader in the circulating fluidized bed combustion of solid biomass waste. But nowadays our portfolio is much more diversified than that. So we have 4 businesses: energy generation, that is all about the combustion of solid biomass waste for production of low carbon, dispatchable heat and power. Circular carbon, the business that I'm leading, that's all about carbon capture and gasification for sustainable fuel applications. Energy storage, there we focus on the large scale, long duration energy storage with a technology called liquid air energy storage that we license from Highview Power, our partner. And all of that is supported by a service business with presence in Asia, Europe, and North America. And altogether with our technologies, we have about 900 references today globally. So this is how we used to, or let's say, like to present our portfolio of solutions in this sustainable fuel ecosystem. So how our solutions bridge the gaps in this value chain from, on the left, the non-recyclable biomass or waste streams and renewable electricity, to the right, to the liquid drop-in fuels. I will not go through this all in detail now, there's no time for that. I will just focus on the gasification part. So we are a supplier of complete gasification islands, including the gasifier and the syngas cleaning. So unfortunately, I don't have a pointer here. It doesn't work in these screens, I guess. But you can see the non-recyclable biomass waste on the left. That is fed into our so-called oxy-steam fluidized bed gasifier, turning that into a syngas composed of carbon monoxide and hydrogen, which is then cleaned and can be fed directly into the synthesis to produce these sustainable fuels, or it can be first mixed with green hydrogen from electrolysis. And then comes the synergy with electrolysis, like EBTL was mentioned already in the previous discussion. So the oxygen byproduct from the electrolysis can be fed into our oxy-steam gasifier, reducing the power consumption of the gasification island. Not to go very much in detail on the technology, but just to show what our value proposition is based on. So at the core of our gasification island, we have this low-pressure oxy-steam circulating fluidized bed gasifier that you can see here. So we feed the solid biomass or waste into the CFB gasifier, into a bed of limestone and sand, which is then fluidized by a mixture of oxygen and steam. And then very simply, the oxygen burns part of the fuel or part of the feedstock to generate the heat that is required to drive the gasification reactions and turn the biomass or the waste into a syngas. And then after the gasifier, you have your hydrogen, you have your CO. Of course, you also still have tars and dust, so there is still a gas cleaning component. Now, why CFB gasifier? I try to sort of list the main benefits that we see from this technology. First of all, CFB gasifier is very versatile in terms of the bio waste that it can handle. Very limited pretreatment required to feed it into the gasifier. And it can handle a wide range of not only biomass but also waste feedstocks. And then the conditions in the CFB reactor are such that the conversion of the carbon in your solid waste or biomass is completely converted into the syngas with almost 100% efficiency. A fluidized bed gasifier is very scalable. We can deliver single line gasifiers up to about 200 megawatt. But I think the most important part of this is that it's a very simple system, and that of course means reliability, and that again means that your plant is available and is making money. So low pressure ensures that we can very reliable feed the feedstock into the gasifier. Oxy steam means that we are directly gasifying the biomass or waste. We are not needing any external heat sources. So it's a very simple system without any external combustor. And also it means that there are no internals in the gasifier. So simplicity, i.e. reliability, that is really the key of the SFW CFB gasifier. Just to show what kind of experience there is with this technology, I just picked a few pictures from the feedstocks that our customers have used in our gasifier. So you can see the traditional woody-based biomass residues from the pulp and paper and the forestry industries. Again, I can't show you the... I don't have a pointer here, but you probably recognize. And then on the right, you see the waste-based feedstock. So on the top, clean waste wood. In the middle, more contaminated construction waste wood. And then raw municipal solid waste. Also special types of waste have been gasified in our gasifiers. Here you can see residues from Tetra Pak recycling, which is a plastic with some aluminium mixed into it, which is then gasified in our gasifier. So quite a versatile technology, a wide range of feedstocks have been utilized, and altogether we have about 40 years of experience with fluidized bed gasification at SFW. We have delivered 11 gasifiers altogether, some pilot plants, some demonstration plants, and a lot of commercial gasifiers, and close to 1 million operating hours today with our gasifiers on biomass and waste. And you can see we already started early 80s providing biomass gasifiers to the pulp and paper industry, mostly for lime kiln applications to replace fossil fuels in lime kilns with fuel gas from biomass. I will not go through all of these, obviously, but I just want to highlight one reference, and that is the so-called NSE Biofuels demo plant. That is an industrial demonstration of biomass to liquids using an oxy steam circulating fluidized bed gasifier of SFW, located at the Stora Enso pulp mill in Varkaus in Finland. So NSE Biofuels is a joint venture of Neste, so a sustainable fuel producer, and Stora Enso, sustainable material producer from Finland. And they contracted with us to deliver the gasification island for this plant, including the gasifier and also the syngas cleaning. And this plant was operated for about 1.5 years in oxy steam gasification mode, accumulating close to 9,000 operating hours with an average reliability of 95%, using the feedstocks that you can see here. So a wide range of these typical woody-based biomass residues from pulp and paper and forestry industries. Yeah, the result was that the technical viability of this technology has been demonstrated now, and it's ready for commercial application. The gasifier is still today in operation as a lime kiln gasifier at the Stora Enso pulp mill, so feeding the lime kiln with a fuel gas from biomass gasification, and has accumulated up to today about 100,000 operating hours. So that is a good basis for a commercial plant as the next step. Now, just to show, or let's say give you a flavor of the kind of yields that can be achieved with biomass gasification in combination with methanol or Fischer-Tropsch. And of course, this is very project specific, and again, this is only to give a flavor of what is possible. Here you have a very simple setup where the required hydrogen to carbon monoxide ratio for the synthesis is achieved by water gas shift. So shifting the CO in the syngas with water gas shift. And then you can see that 300,000 tons per annum of wet biomass is converted into methanol with about 50% mass efficiency and about 60% energy efficiency. And then for SAF, the numbers are about 20% for mass and about 50% of for the energy. Now this can be optimized. EBTL was already mentioned as a term. So that is what we see very much in the market at the moment. Typically in the forecasts, power to X and gasification are sort of put against each other as competitors, but actually they work together. So we can replace the water gas shift by adding hydrogen from electrolysis to the syngas to significantly boost the yields, or of course significantly lower your biomass consumption for a certain amount of biofuel. So here you can see that with a 40 megawatt electrolyzer added to this setup, you boost the yields with about 30% compared to the previous slide. That you can also further optimize if the electrolyzer is sized to produce all the oxygen that is needed for the oxy-steam gasifier. Then you would need a 120 megawatt electrolyzer in this case, and the yields go up with about 60% compared to the base case that I showed earlier. Okay, so what are we concretely doing at the moment? It was already mentioned that FIDs are missing at the moment. That is true, but the market is extremely active, both in Europe and in the US and also Australia. And this is a typical project that we are working on together with a customer. In this case, Capot, a customer in Portugal, developing a green methanol project, the so-called Mangualde renewable methanol project. And they selected us as the gasification technology partner for this project in Portugal, which when it's in operation will produce 80,000 tons per annum of renewable methanol from locally sourced biomass residues. And again, with this hybrid concept, using also green electricity from a nearby PV solar farm. This is currently in the so-called FEED stage that we are working on at the moment to underpin the FID of the customer later this year, hopefully during autumn. Another project going to Texas in the US, where we are working with our customer Pathway Energy on their GT project, which is a big project. I mean, the methanol project was relatively small. This is a much bigger project like SAF projects tend to be. And this is a very interesting project because it combines a lot of elements that you can see here. It combines bioenergy with carbon capture and storage, so-called BECCS, to produce carbon negative renewable electricity to power the biorefinery, which is a gasification to liquids concept using our gasifier and a Fischer-Tropsch process to produce SAF. And of course, like already mentioned, a carbon capture and storage element to put the CO2 under the ground. So when this plant is in operation, which of course is still a few years ahead of us, the FID is due sometime later this year, it will produce carbon negative SAF of about 2,400 barrels per day with a carbon intensity score of minus 300 grams of CO2 per megajoule. Now we are not only selected for the gasification island, but we are also providing the so-called oxy-fuel combustion technology that we have developed at SFW for the BECCS plant. So that is a technology that uses a mixture of oxygen and oxygen and carbon dioxide, of course, for combusting a biomass and thereby producing a flue gas that is 90% CO2, which then needs to be dried, of course, purified, and then can be compressed for storage. Then a little bit at the end, this is the last slide, just to show what kind of scope we provide as SFW. So this is the same scope for both the Capot project and the Pathway project. So we We are very versatile. We can help support methanol projects, SAF projects, green renewable natural gas projects with this kind of scope. So again, I don't have a pointer here, but maybe you recognize at the core the CFB gasifier, turning the biomass into a raw syngas, which is then cooled in the raw syngas cooler, going to a filter to take out the dust, take out the corrosive components, after which it goes to a reformer, which then cracks the tars that are still in your syngas into smaller molecules, into carbon monoxide and hydrogen, after which you have a dust-free, tar-free, corrosive component-free syngas, which is then further cooled and going to the final cleaning step, which is a conventional scrubber to take out the ammonia, sulfur, and chloride compounds. And then you're ready to put it into your syngas compressor to lift up the pressure to the level that you need for the synthesis. With that, I would like to thank you very much for your kind attention. And if any questions arose already now, then please shoot. If not, if later, then welcome at our booth E18, which is over there somewhere. So, yeah, thank you.
Thank you, Frank. Some questions from the audience? Okay, yeah. No. So maybe I have a question for you. You have presented lots of feedstock that you can feed your system. You have polymers, you have biomass. Maybe you have different contents of moisture and of minerals. So how can you deal with this variability in the process?
Yeah, that's a very good question. I mean, so we are using a circulating fluidized bed process for the gasification, and that is the same process that we use for our CFP boilers. So we have about 550 references of big CFP boilers burning a wide range of solid fuels, typically as a mixture of different types of fuels, waste and biomass burned in the same boiler. So this CFP process is inherently giving you a lot of flexibility for the feedstock. It's the conditions in the reactor that you have this vigorous mixing of the feedstock, the bed material, the heat, the fluidizing medium that gives very good conditions for optimal conversion. And then you have this circulating bed material which acts like a thermal wheel with a high energy content. So the energy that comes in with the biomass is actually very small compared to that thermal wheel. So that makes the process inherently insensitive to variations in your feedstock, in your feedstock quality, and therefore you can guarantee a constant quality of the syngas going out of your CFB gasifier. So it's really the CFB process which has this superior mixing of all the components in the reactor. That's the key.
Okay, thank you.
Thank you for this nice presentation. What is the pressure of the gas out the outlet of
yeah, so what I mentioned is that we try to keep things very simple, because that means that your system is reliable. So we are offering a low pressure gasifier. Of course, you need to be above atmospheric pressure to overcome some of the pressure drops in the syngas cleaning. But let's say at the interface with the syngas compressor, you are a little bit above atmospheric pressure, maybe 100 millibar. Having said that, we also have a lot of experience with pressurized gasification. We actually we built the first integrated gasification combined cycle unit with a pressurized gasifier at 18 bar absolute. So we are very wise in that sense, and that is one of the reasons why we actually recommend not to increase the pressure, to keep, again, things simple. These are first of a kind projects where you already have a lot of other issues to deal with, and you don't want to deal with the technology risks of going to high pressure. So we typically offer low pressure gasifiers. Yes.
Okay, thank you.
Thank you, Frank. We'll stop here for the moment, then we can take back during the discussions. Now we have Antoinette Maarawi. She's a postdoctoral engineer at the CEA Liten. Okay, she has a PhD in chemical engineering, and she's currently working on the carbon capture and utilization, mainly in Power-to-X applications using catalytic reactors. So her expertise covers both experimental and numerical aspects, including pilot scale trials and reactor modeling. So now she will be presenting her presentation on the direct hydrogenation of carbon dioxide to produce liquid hydrocarbons, and the application is to sustainable aviation fuels. So you will present in French, I think. Okay, so thank you, Antoinette.
Bonjour à tous, merci Sari pour l'intro. Thank you. Je suis Antoinette Maarawi, donc je travaille au CEA Liten à Grenoble sur l'hydrogénation directe du CO2 en hydrocarbures liquides. Donc je vais commencer par un contexte général avant d'aller particulièrement aux résultats de ces travaux. Donc nous avons tous en tête la volonté d'aller vers une neutralité carbone en 2050, tout en réduisant nos émissions en CO2 et gaz à effet de serre. Donc dans ce contexte, s'inscrit la mise en place d'une économie circulaire de carbone, l'ECC, à laquelle le CEA s'intéresse pour accélérer la transition énergétique. Donc c'est quoi l'ECC, comme vous savez tous? Donc c'est l'ensemble de technologies de transformation du CO2 à partir d'énergie bas carbone en produits synthétiques utiles. Ça marche. Utiles dans les secteurs d'énergie, de chimie et de transport. Donc là, on parle particulièrement du transport et donc des carburants d'aviation durables, les Sustainable Aviation Fuels. Donc, comme on connaît tous, il y a la réglementation Refuel pour l'aviation. Donc l'Union européenne impose d'augmenter la part de ces SAF dans les carburants conventionnels jusqu'à atteindre 70% en 2050. Comment on fait ces SAF? Donc il y a plusieurs procédés. Il y a le procédé biomass to fuel pour produire ce qu'on appelle les biocarburants. Donc c'est à partir de la gazéification de la biomasse. Et le CEA travaille sur ce sujet. Donc je vous invite aussi à venir nous voir sur notre stand D28 pour que mon laboratoire, donc mes collègues dans le laboratoire qui travaillent à ce sujet pourront vous fournir plus d'infos. Après, je passe au procédé Power to Fuels pour parler des e-carburants. Là, je reviens vers la réglementation de l'Union européenne qui impose d'avoir 35%, donc d'incorporer un minimum de 35% de ces e-carburants dans les réservoirs d'avions en substitution du kérosène fossile d'ici 2050. Donc, c'est intéressant, donc on s'intéresse plus à ce procédé et donc je vais vous présenter plus particulièrement ce procédé. Donc ici, les e-carburants sont produits à partir du CO2 qui peut être capté directement de l'air ou des fumées industrielles ou même de la biomasse. Il sera combiné à de l'hydrogène produit par l'électrolyse de l'eau à partir des énergies bas carbone. Donc je travaille particulièrement sur cette combinaison, donc cette réaction catalytique entre les CO2 et l'H2 pour produire ces e-carburants. Donc cette réaction d'hydrogénation directe du CO2, donc c'est la Fischer-Tropsch modifiée à partir du CO2, se fait en deux étapes. Donc la première étape, c'est de convertir le CO2 en CO, c'est la RWGS, Reverse Water Gas Shift. C'est une réaction endothermique, donc qui nécessite de la chaleur. La deuxième étape sera de convertir ce CO en hydrocarbures liquides, donc par Fischer-Tropsch classique, traditionnel à partir du CO. Et c'est une réaction qui dégage de chaleur, donc exothermique. Donc ces deux étapes peuvent se faire séparément dans deux réacteurs en série, donc c'est la voie indirecte. Mais cela, puisque ces deux réactions se font à des conditions de pression et de température différentes, on a besoin d'étapes intermédiaires, de compression, de refroidissement. Et du coup, ça augmente le coût énergétique, mais pas que ça. Donc ici, le verrou, c'est le bilan thermique, mais aussi la faible conversion en CO2. Donc ce qu'on envisage, c'est la voie directe. Les deux étapes se font dans un même réacteur. Et cela pour augmenter l'efficacité énergétique du procédé, mais aussi pour augmenter ou améliorer la conversion en CO2. Donc pour cette réaction, pour l'étudier, donc comme pour toute autre réaction, on a une stratégie qu'on suit dans l'équipe, dans le laboratoire. On commence par des tests expérimentaux pour mieux comprendre la réaction. Donc c'est une recherche des phénomènes, donc phénoménologiques, pour comprendre la réaction, donc avec un certain catalyseur, pour en tirer des données qui peuvent nous aider à faire un modèle cinétique qui est représentatif de la réaction, qui nous permet de savoir la distribution des produits, donc la formation des produits à partir de la réaction. Puis ce modèle cinétique sera intégré dans un modèle réacteur. Donc là, il y a un couplage entre la partie expérimentale et la partie modélisation. Pour, après, à l'issue de ces résultats, donc là aussi, il y a la validation du modèle par les résultats expérimentaux. Donc il y a toujours des allers-retours entre ces deux briques-là. Et tout cela pour orienter le design du réacteur et arriver à une technologie de réacteur adaptée à la réaction envisagée. Donc là, je vous montre un démonstrateur réacteur d'hydrogénation du CO2 en méthane. Et aussi, donc, je vous invite encore une fois, donc je fais la pub pour notre stand D28. Vous pourrez venir nous voir pour en discuter plus à propos de cette technologie, mais aussi à propos de notre stratégie qu'on suit pour l'application envisagée. Je reparle particulièrement de l'hydrogénation directe du CO2 et du coup, je vous parle des tests expérimentaux. Donc pour commencer, on a des premiers résultats qui étaient obtenus dans l'équipe avec un catalyseur qui était fait maison, donc à une petite échelle. C'est un catalyseur à base de fer, dopé de potassium, supporté sur alumine. Donc il a été testé dans un réacteur tubulaire à l'IFPEN. On a obtenu des conversions allant jusqu'à 30% en CO2, après une sélectivité de 10% en CO. Et puis dans les hydrocarbures, on produisait plus de méthane et de l'effine courte. À l'issue de ces résultats, un modèle cinétique a été développé donc, pour ce catalyseur. Pour aller plus loin, donc essayer d'améliorer la sélectivité, pourquoi pas travailler sur la technologie de réacteur. Donc, ce que j'ai fait, c'était dans le but d'évaluer l'effet du design du réacteur sur les performances de cette réaction. Donc, en prenant comme point de départ le catalyseur qu'on connaît, on le synthétise à une échelle plus grande par un industriel. Donc on a un catalyseur upscalé qu'on teste dans le même réacteur. On trouve des résultats différents de ce qui était obtenu avec des conversions supérieures à 30%. Donc ces différences de résultats nous poussent à faire de nouveaux tests avec ce catalyseur upscalé pour développer un modèle cinétique spécifique pour ce catalyseur. Donc pour ce faire, j'ai varié différents paramètres de la réaction pour voir l'effet. Donc la température entre 250 et 310 degrés, la pression totale jusqu'à 20 bars et le ratio hydrogène-CO2 à l'entrée du réacteur entre 3 et 12, et puis le temps de contact, le taux mode, qui est la masse du catalyseur par rapport au débit des gaz entrants, pour voir l'effet sur la réaction. À l'issue de chaque test, il faut analyser les produits. Donc on analyse la phase gaz, la phase organique et la phase aqueuse pour identifier et quantifier les produits obtenus. Donc parmi ces différents paramètres, je n'ai pas le temps de vous détailler tous les effets, mais je vais parler de deux effets. Donc l'effet du temps de contact au début. Donc là, si on va dans le graphe qui est à gauche, on a la conversion du CO2 qui est en bleu, qui augmente avec l'augmentation du temps de contact. Et aussi, on diminue la sélectivité vers le CO progressivement en augmentant ce temps de contact, tout en ne pas bougeant la sélectivité vers les CH4. Donc là, ça nous permet de dire que la réaction Fischer-Tropsch est limitante et la conversion de CO en hydrocarbures est favorisée. Donc pour voir les hydrocarbures, on passe au graphe qui est à côté. Donc on voit une influence sur la sélectivité vers les C5+, par exemple, en particulier, là on s'intéresse au C5+. On voit que ça augmente avec l'augmentation du temps de contact. Donc on a intérêt à augmenter le temps de contact si on veut augmenter la sélectivité vers les C5+. Après, concernant la température, donc en augmentant la température, on augmente la conversion, en diminuant aussi la sélectivité en CO, mais on produit un peu plus de CH4. Et du coup, la température a un effet sur les deux étapes de réaction, mais ça active de plus la Fischer-Tropsch, puisqu'on diminue la sélectivité en CO. Concernant les produits, donc, on voit quand même une augmentation des C5+, avec la température. Donc, on a aussi intérêt à augmenter la température, mais à ne pas trop l'augmenter aussi, pour ne pas désactiver le catalyseur. Donc, d'après ces deux résultats, on pourrait dire que pour augmenter le temps de contact, qu'est-ce qu'on peut faire? On peut diminuer le débit à l'entrée du réacteur, mais on diminue la productivité. On pourra augmenter la quantité du catalyseur qu'on utilise dans le réacteur. C'est faisable avec ce catalyseur qui est peu coûteux, mais il faut faire attention. Si on augmente l'épaisseur du kata dans le lit catalytique, il faut faire attention à la contrainte thermique pour ne pas avoir des points chauds. Donc tout cela nous permet d'orienter le design du réacteur et penser à un réacteur qui nous permet de bien gérer la température, mais aussi, pourquoi pas, avoir un réacteur qui nous permet de prolonger le temps de contact et du coup le trajet du gaz dans le lit catalytique. Donc je passe par la suite à un paramètre qui est important, c'est le alpha. C'est la probabilité de croissance de la chaîne de l'hydrocarbure formée. Donc plus le alpha est élevé, plus on produit des chaînes longues. Donc ce alpha peut être obtenu à partir de ZI, qui est la fraction molaire de chaque produit formé. Donc si on revient à la littérature pour voir les procédés Fischer-Tropsch à partir du CO, pour des catalyseurs à base de fer, donc dans la gamme de température, donc en bleu, dans la gamme de température qu'on étudie, les valeurs de alpha sont entre 0,7 et 0,8. Si on regarde ce qu'on a obtenu dans la partie expérimentale, on a des alphas qui sont entre 0,7 et 0,73. Donc là, les alphas obtenus sont pour la réaction Fischer-Tropsch modifiée à partir du CO2, sont dans la gamme des alphas obtenus à partir des procédés Fischer-Tropsch du CO. Donc ça, c'est vraiment un résultat très intéressant qui nous dit qu'on réussit à produire à partir du CO2 ce qu'on produit à partir du CO. Donc, par la suite, avec toutes ces données, on a pu développer un modèle cinétique pour ce catalyseur upscalé et on l'a intégré dans un modèle du réacteur tubulaire, un modèle 2D. On a fait des simulations et on remarque que dans certains cas, il y a une élévation de température qui peut dépasser les 15 degrés, ce qui est aussi observé expérimentalement, mais cela affecte négativement la sélectivité vers les hydrocarbures à chaîne longue. Et du coup, une fois aussi, on est sûr qu'on a besoin d'une technologie qui est capable de mieux gérer la température du lit catalytique. Cela nous a poussé à penser à un nouveau réacteur millistructuré qu'on a modélisé pour surmonter cette contrainte thermique. On a développé des modèles 2D puis 3D avec le modèle cinétique intégré. Et là, on a obtenu, au lieu de 15 degrés, moins de 1 degré C d'élévation de température dans le lit catalytique, tout en conservant les performances en conversion et en sélectivité. Donc ça, c'était un résultat intéressant qui nous a poussé encore à optimiser le design de ce réacteur. Et là, on trouve un delta T de 3 degrés C qui reste toujours acceptable en ce qui concerne l'effet sur la sélectivité des produits, mais on a obtenu aussi des performances maintenues, mais on a doublé la productivité. Donc là, à nouveau, on voit que ce nouveau réacteur, il est prometteur et ça mérite d'être encore optimisé avant d'utiliser ce réacteur pour cette réaction de Fischer-Tropsch directe à partir du CO2. Je passe aux conclusions. Donc, pour la partie expérimentale, un catalyseur upscalé a été testé et les effets de différents paramètres ont été étudiés sur la réaction, sur les performances de la réaction, pour mieux comprendre et orienter le design du réacteur. Après, un résultat qui est intéressant, c'était les valeurs de alpha obtenues qui étaient dans la gamme des alpha obtenus pour des procédés Fischer-Tropsch traditionnels. Un modèle cinétique est développé et intégré dans la partie numérique. Donc là, on voit les allers-retours entre la partie expérimentale et la partie numérique. Donc on a un modèle avec des résultats prometteurs pour un nouveau réacteur structuré, mais ça nécessite encore des validations expérimentales. Tout cela nous mène à faire aussi des études de sensibilité dans le modèle numérique pour varier les paramètres géométriques de ce réacteur, de ce design, pour optimiser le design de réacteur et aller à une proposition de technologie plus adaptée à cette réaction d'hydrogénation directe du CO2. Merci et n'hésitez pas si vous avez des questions.
Thank you, Antoinette.
capacity constraints in the grids today. So this isn't really working. And if we look at Germany, running that process on 26 million tons of waste produces how much electricity for the German energy system? 2.4%. So almost nothing. And that's why incineration is the fax machine of waste management. I don't have a fax on my desk. I don't know about you. If we go back to the chemistry then, we crack instead the hydrocarbons into hydrogen and CO2, which is captured. We have zero ash. Instead, we have a slag material that can be used as a construction material. Oops. But there's no hydrogen economy. So what do we do with this hydrogen? One thing we need to do is we need to go into sector coupling. We need to change the way we think about energy. We need to use the resources that we have in new and innovative ways. Another example of sector coupling is two actors buying a football team to start a TV series. If we go back to energy, you've all seen these charts all over the place. The only problem is that the efficiency is very poor. It's often large scale and it's infrastructure dependent. If we go back to the incineration systems, yes, you can add some wind, you can add large scale solar. The only sector coupling going on is power to heat pumps, still coming from the grid. And then you have the SAF, the e-chemicals, which you can do from power, but you need to find the CO2 somewhere, and that's often a challenge. If we go back to the chemistry and the gasification, we can deliver speed charging. I'll talk about that tomorrow. We have local green heat and thermal cooling as a byproduct. For the circular chemicals, the SAF, we can take the hydrogen straight from the process, and we have our own CO2 captured that we can use in the process. And the result of that, yes, the production cost is fairly high, but now comes the interesting part. We have byproduct revenues. We charge a gate fee for our fuel, that we receive for taking care of it. We can sell the excess CO2 as a replacement of fossil CO2 in industrial processes. We can sell the heat if we pick our sites well. And as a result, we end up with a production cost that is very close to the fossil. And depending on the various processes that we use, it is conceivable to get that even further down to below the fossil price. And keep in mind here, I have not included carbon, various types of carbon benefits in this here. So that comes on top. Just to illustrate the sector coupling here, if I have 1 megawatt hour of power, I can produce 17 kilos of hydrogen. I have a ton of waste, run it through electrolysis, an incinerator and electrolysis, I get 10 kilos, adding up to 27. On our side, we use gasification. If I self-power and use some of the hydrogen for parasitic power in the system, I get 50 to 60 kilos of hydrogen. Now, if I instead use that megawatt hour of power for my parasitic load, I get a full 100 kilos of hydrogen out. So the interesting thing here is that using that megawatt power in our process gives you 50 kilos of hydrogen compared to only 17 if you run it through electrolysis. That is the nature of sector coupling. Okay, so how did we bring this from science to technology? Gasification of waste is difficult, but it can be done if there is a deep understanding of waste, of high temperature chemistry and energy systems. We have developed a technology that has a high tolerance for waste quality variations. It's a simple gravity-driven, no moving parts. It's a slow process that allows chemistry to do its thing. We're not rushing chemistry. We have a high energy conversion rate, carbon capture, and as I said, no residues. We've developed this technology from lab scale up to industrial size. We're now going in the technologies that we're developing up to TRL9. We're going to commercial size, which is 2 tons per hour per reactor. Every system has 2 reactors running and 1 on standby. How do we do this? Yeah, we leverage partnerships to get the complete system done. Our principle is to not reinvent anything. So we focus on the reactor system, gets that running to produce syngas. All the upstream systems are commercially available technologies that we bring in from partners. All the downstream systems are commercially available technologies, not all the SAF technologies yet, but it's coming there. These are also delivered by global technology partners, and that gives us unlimited capacity to scale from day one. We have a 300 plant rollout plan together with Siemens. Not all of those will be SAF. There will be charging as well and other solutions. And that's how we roll. We're developing a number of projects, some of them green chemicals, SAF, some of them charging, and that's what we're doing. Thank you.
Okay. Thank you for your presentation, Heike. Any questions in the audience about this new technology? Maybe I have a question about the carbon footprint of the, since you are dealing with wastes, we see in the waste there are good part that are fossil-based, like plastics, tires, textile. So how they are accounted for, and how can we judge from the mix at the inlet that we are respecting the sustainability criteria for the fuels?
Yeah, exactly. So we're dealing with waste, not biomass. So as you say,
Yes.
part of it is fossil. It's typically around 50%. So all of it will be captured. And then the fossil part can either be stored or sold as circular CO2, which is still better than fossil CO2 generated only for the purposes of greenhouses and various chemical processes. And the green part then is used for fuel production. So this will be audited and monitored by third parties, etc. So there is a, yeah, so we make sure that we don't produce more than the green CO2 allows. Yeah.
Okay, so you calculate the fraction of fossil part and you sequestrate it.
Yeah.
Okay, but in the European regulation, they are, and the SAF that's intriguing a little bit is they consider the recycled carbon fuels as part in the SAF. So typically these wastes are recycled carbon fuels. So
yeah,
how they are accounted for exactly?
It can be allowed as well. We're somewhere in between recycled carbon fuel and low carbon fuel. The only thing we know is that we're not an RFNBO because it is of biological origin. So, but it's still floating a little bit, these regulations. They are on their way. Yeah.
Okay. So with the technology that you are applying for these wastes, so what's the technical potential from the 4 billion tons of waste that that our children will see? What's the potential of of this.
How much of that can
could be, yeah, the technical.
Yeah, I mean we haven't spent a lot of time on that. What we have done is our technology is developed to basically be able to handle the rest. So if you have a homogeneous flow or a homogeneous stream of waste, then by all means go pyrolysis but for the non-recyclable stuff, the things that changes a lot, our technology is specifically developed for that because it's a slow process. A waste particle will spend 8 to 10 hours in the reactor. So, which means that there is time for everything to disintegrate and to react. A lot of other gasification processes are very fast, so you require a large amount of shredding to 2 by 2 centimeters or something. We have 20 by 20 centimeters, and the process itself is designed. So what also happens then is that the variations in the syngas quality are quite low, because if I have 10 tons of waste in the reactor and I add 250 kilos every once in a while on top, the total calorific value of the mass of waste in the reactor doesn't change that quickly, so the system has time to react. We also don't try to produce anything straight from the syngas. In theory, yes, you can do things straight from the syngas, Fischer-Tropsch and other things, but experience shows that it's very difficult to handle the variations. There will be variations, so we go all the way to hydrogen and CO2, and then we kind of back up from there. But it's the way we do it to make sure that it works. So.
Okay. No questions from the audience? No?
And what I can add on the gasification side as well, because we get that question a lot. Like, okay, so people have been talking about gasification for decades. Why, and it never worked. Why will this work now? So part of some of the technical choices that we've done, we're obviously standing on the shoulders of a lot of failed gasification projects and a lot of learnings from there. And what we typically say now is that gasification has reached its Tesla moment, basically. We had electric cars for 100 years. It's just that the battery wasn't good enough. There was no charging. The drivetrains were not good enough. But all these things, due to other factors, mobile phone development, all kinds of things, when Tesla came into the game, the batteries were pretty much there. The drivetrains were pretty much there. They realized the need for charging, and they put together a system that actually works. And boom, we have electric cars. So that is where we feel like gasification is today.
Yes, just one question. If I'm not wrong, the main part of a reduction of a price from the beginning is coming from fees.
Yeah.
Do you think it's a sustainable model?
Yeah, it's yes, it is. I mean, gate fees are just going up. Gate fees are at very different levels in different markets, of course. So in emerging markets, etc., gate fees are typically lower, but they are still not low. And waste is becoming a big issue. And just kind of thinking that it will happen on its own and just kind of being taken care of, it doesn't really exist. But we don't account for a very high in our kind of longer term scenarios. We're conservative in our assessment of the gate fees. Yeah.
Thank you. Thank you, Heike. Okay, now we will move to the discussion, open discussion with all the speakers. So You can start with the questions from the audience about the SAF, the application, the gasification technology, and the Fischer-Tropsch maybe. Maybe I will, I will go back to the last point raised by Heike about the gasification and the fact that, there are lots of projects, lots of research that was done on gasification and Fischer-Tropsch to produce SAF. So I want to also hear the other panelists' opinion about the maturity. What are you described it very well when you made the analogy with the electrical car. So what are the hurdles today to get to these processes to the market maturity, to the market application? I don't know who wants to start. Maybe Frank. Yeah.
This work? Works? Maybe this works?
Yes.
Yeah, of course, I would say that the technology is already mature, but that's because we have worked on it for 40 years and we have demonstrated it. But I think, I mean, if I interpret your question correctly, that what are sort of the obstacles to make this all happen? And well, our limited perspective from working with customers that we see it's a very entrepreneurial market still. So the projects are being developed by small project developers without a balance sheet. They need a lot of development funding, sometimes 50 to 100 million euro, just to bring the project to financial closure. And it's difficult to get the financing. So I think what is missing from my perspective is that it's not yet mandatory. So the big companies, the big oil and gas companies, the airlines and the shipping companies, they are still reluctant to become involved in investing in these projects, and they need to become part of the game if they want to get these sustainable fuels at some point in time. So yes, these are first of a kind projects. I do think that the technology is mature enough, but there is this enormous risk perception that makes it very difficult to finance these projects. But maybe some additional views here, or
yeah, I agree. What we see is there is when you come to a 1 billion investment, for sure, you have to be sure that it will start producing very fast if you want to get your money back. And that's we are also very, very conscious on that, and that was the purpose of these big demo plants. What you provide also hours of operation and see very early what will be the problem. We see, for instance, the difficulties got by Fulcrum in the US. That's a bad example of what you want to see. And obviously, we have seen also some difficulties in our demo plants, and thanks to that, we improve the design, the preparation of a feedstock also with major points, and to be ready to start on. And it's true that it gives confidence also for people who want to invest to see this de-risking step.
So from technical point of view, there are no obstacles. It's really, let's say, economic risk that is the major problem.
Yeah, I mean, if you ask if you ask us, the technology is ready. We've proven it in a full-scale plant, etc. But the waste management industry has been burned to some extent on this as well. I mean, we talked to a Belgian incineration operator, and I ran into the chairman at an event, and he's like, "Oh yeah, we're thinking about it," but you have to understand that the first pitch, I heard the first pitch for gasification in '85, and it still isn't there. So it really takes a lot of convincing. That's why we work with partnerships. We work with Siemens. We work with other big players, so that a customer can feel that, okay, even if these guys don't exist in 5 years, I can still get the gear serviced and run and maintained.
Okay, Antoinette, maybe you have.
I will talk more about the efficiency of each process. For example, in the biofuel, the production of biofuels, the real problem is that we do not valorize all the carbon that is contained in the biomass. And for the e-fuels, the problem is we need electricity. So in both we have pluses and minuses. But why not do the e-biofuels and combine the advantages of both processes in order to take advantage of the carbon that is lost in the biomass and take advantage of the energy that is contained in the biomass. So I think this can be a solution in order to have more of the biofuels, and we should work on this. We should work. There are regulations that are really forcing the presence of SAF or biofuels. So we need to optimize, keep working. We should be optimistic really about this subject, to keep working on this and optimizing all the process, the electricity, the capture of CO2, and why not working on the combination of both processes.
Okay, so what about the collection radius for the smallest unit that could be economically viable? Will you collect the feedstock on 50 kilometers, 130 kilometers? What are the typical ranges for these to have a viable?
Yeah, on the waste side, this particular port project, which is here, that's 220,000 tons per year. Our standard unit is, and that's kind of the good size for methanol production. Our standard unit is 100 tons per day, so 36,000 tons per year. That's about 100,000 people.
Okay.
And our idea is to be as distributed as possible. Those smaller scale technologies for doing chemicals, they're on their way. So we think that by the time we're on the market, we should be able to do this at fairly small scale.
You have any, or let's say the smallest scale or power that you estimate that it's viable, economically viable? Because I think one of the hurdles, also one of the obstacles, is the size of to be viable. We should have big size of.
Absolutely, I guess it's sort of a dilemma, because basically, like you said, you need the economy of scale to be economical. But then again, you are talking about 3-4 billion euro or US dollar investments for SAF projects, which is quite typical in the US. So we, these are first of a kind projects again. So maybe the first one, you should be a little bit modest and not target for the 4 billion US dollar project. So the project we are working on now in Portugal, this methanol project, 80,000 tons. So that is sort of on the lower end of what is still economically viable. But then again, it depends really on what the shipping companies are then willing to pay for the methanol. What are the incentives for them to do so, and what are the mandatory blending mandates that will be applied? So it's a combination of legislation, incentives and all that kind of things to make it happen. But certainly small projects are difficult to make economically viable.
Yeah, coming from the question of incentive, I think it's very sensitive for the SAF. Typically, we see that there is an opportunity, but there is also some risk coming on uncertainty of regulation. The big picture is quite clear in Europe, but when you look at details and how it will be sustained over time, especially the accountability. You talk about recovered solid fuel, but it's a little bit the same with the SAF. For instance, for the RFNBO, it's very. It means it gives some constraints on the flexibility of units, flexibility for Fischer-Tropsch option or RWGS is not an easy thing. And for instance, in France, we are lucky to have electricity which is quite decarbonized, thanks to the CEA in parts and our nuclear industry. So this is a real opportunity. But yes, the accountability for the CO2 reduction is really linked to the way it is accountabilized by the European Union, and then we are strongly dependent on regulations for that. So that's an opportunity and a risk also for the development of BioSAF in Europe.
Okay, so if I get back to the to the main problem with the investment risks, so what can the European Union do, or what in the research and development we can do in order to maybe reduce the initial capex or the initial investment to diminish the risk, or on the other part have to ensure that the investor that the 1 million that they have invested will get their fruits at the end of the project. So from regulatory and from research and innovation, you choose what.
Yeah, I mean the EU is pretty slow. There was recently they had this regulation out for review or for feedback in November, December, and about how to calculate the carbon footprint of something, and I mean we spent a fair amount of, and we work with this. We spend our days doing this, and we based on their draft, we couldn't figure out our own kind of carbon footprint. So it's extremely complicated. And then you have various EU institutions that kind of apply different principles. Some are a little bit stricter, some are not. And the EIB is not looking at things the same way that the EU is, and stuff like that. So it's a bit of a mess. And I think if Europe doesn't get their act together, to use an acceptable word, I mean, a lot of things will just move elsewhere, where where things are moving a bit quicker and people are a bit more action oriented. Having said that, the last time when I was doing a number of panels when the U.S. when the Biden administration launched the IRA, and there was an NG guy on one of my panels, and he said, like, yeah, we have a lot of clients and partners that are now froze their investments in Europe and are starting to explore the US. And this is maybe 3 years ago. I don't think those projects got off the ground, and neither ARA is probably gone as well. So it just speaks to the need to try to build business cases and technology that works on a commercial basis, on commercial terms, and to not build businesses solely on where can I get the support for this. And I think that's very important and something. It's not easy, but to cherry pick the projects and to cherry pick things to make sure that you get off the ground in a way that is on some level commercially viable.